Welcome back to our lectures on the constitutive modeling. Till the previous class, we were looking at the linear elastic and then the bilinear elastic model, and then bilinear elastic models we have seen in terms of the tangent shear modulus and then the bulk modulus, or the tangent Young's modulus and the bulk modulus. And the advantage with those models is that we were able to put a limit on the loads that we can apply by introducing the Mohr Coulomb yield criteria on the shear stresses. The advantages of these models, it is a very simple model, either KG or EK model. They are very simple and they are able to represent the limit state of soil and all the limit solutions like the bearing capacity of soils or the lateral earth pressures. All these can be evaluated accurately using this simplistic model, but several limitations are there. The modulus is not a function of the confining pressure. See, this is one of the most important features of the soil. At a higher confining pressure, the soil will exhibit a stronger response in terms of the strength and also a stiffer response in terms of the modulus, and that we are not able to simulate by using the bilinear elastic model. And these models are unable to simulate the volume expansion. And another disadvantage is that these models are unable to simulate volume expansion under the shear strains. That is another major feature of the soils, and that we will see later. And the strain hardening and strain softening are not simulated by these bilinear elastic models. And then the accuracy of the solution very much depends on the strain increment that we use, on the load increment that we use. And we have seen with the some numerical examples of the simulation of the triaxial compression test that with the coarse strain increments we over predict the limiting stress by an order of even 50%, 60%, and to get reasonably accurate results we have to use very small strain increments, and that will increase our computational effort and also the time. And so we need to come out with better solution methods for improving our modeling capabilities. And in that direction we have the nonlinear elastic models. These are still elastic but nonlinear, and one of the simplest nonlinear elastic models are the variable moduli models, and then we have the hyperbolic model and then modified hyperbolic model. And of course there are several other intermediate type of models that I am not going to discuss because of time limitations, but then I will give you some references that you can refer to for more details. See, one of the simplest variable moduli models was proposed by Nelson and Barron in 1971 for modeling of the railway ballast, and they formulated the constitutive matrix in terms of tangent bulk modulus KT and then tangent shear modulus GT, and KT is expressed in terms of three parameters K0, K1 and K2, like KT is K0 plus K1 I1 plus K2 I1 square, and then GT is G0 plus G1 times J1 plus G2 times J2D. And in these the I1 is the first invariant of strain tensor epsilon XX plus epsilon YY plus epsilon ZZ, and if the volumetric strain is compressive, the volumetric strain is positive, and that is our geotechnical sign convention. And so, if you look at this equation, as long as you have volumetric compression, your bulk modulus is only going to increase, because it is k naught plus k1 I1 plus k2 I1 square, and of course, I1 square will be very small compared to I1, and then the shear modulus is expressed as G naught plus G1 times J1, and J1 is the first invariant of a stress tensor that we had seen earlier as sigma xx plus sigma yy plus sigma zz, and J2d is the second invariant of the deviator stress tensor. If you remember, or if you recall, we had split the total stress tensor into two parts. One is the spherical stress tensor, in which all the stress matrix is a stress tensor is a diagonal tensor with only the diagonal terms, and all of them are equal, and that represents the hydrostatic stress state. And then we have the other component, the deviatoric stress tensor, and J2d is the second invariant of that deviator stress tensor, and deviator stress tensor represents your shear stresses, and our KT and GT, they continuously change during the analysis, and so as long as your volumetric strain is compressive, the KT will go on increasing, and if I1 is tensile, our bulk modulus will reduce because I1 becomes negative, okay. And then our J1 is representing our volumetric compressive stresses, and because of that, the effect of the volumetric compressive stresses is to increase the shear modulus. Then J2d is the second invariant of the deviator stress tensor, and if you recall, that is written as 1/2 of Sij multiplied by Sij term by term product, and J2d is a positive quantity because it consists of all the square terms, and the parameters k naught, k1, k2, g naught and g1 are positive in value, or kt and gt should increase with I1 and j1, and then our as the shear stresses increase in magnitude, our shear modulus should reduce. So, if we determine our parameters, we will see that G2 is negative, and that is the only negative quantity of all these material parameters. And when we say these, when we refer to these variable moduli models, the material parameters are k naught, k1, k2, g naught, g1 and g2. Let me just turn on the laser pointer. Okay. So, these are our material parameters, and one reason why these models have not become very popular compared to other models that we will see later is this k naught, k1, k2 and all these parameters, they have no geotechnical context. These are obtained by regression analysis of the stress strain and volumetric strain curves, and so if I give you the values of these parameters, you will not be able to tell whether the given soil is a loose sand, dense sand or a clayey soil or any other attributes of the soil. We cannot guess by looking at these parameters, and so that is one reason why although they were developed, they have not become very popular in the context of geotechnical engineering, and that is when other models started coming in. And these variable moduli models, they are elastic models, and hence they will not be able to simulate shear induced volume expansion, that is dilation, and there is no failure criteria associated with these variable moduli models. There is no failure criteria like what we had seen in the case of bilinear elastic models. We had used the Mohr-Coulomb yield criterion for putting a limit on the shear stresses, but here there is no such limit, and our the K0, K1, K2, G0, G1 and G2, they automatically take care of the failure, because these are actually determined by regression analysis of the given stress strain curves. And because of these reasons, mainly because there is no failure criteria that any geotechnical engineer can easily appreciate. It is a Mohr-Coulomb model, means every geotechnical engineer will know. If you give the C and phi, then we can know what type of soil we are dealing with. If there is a predominant cohesion, then we know that the soil is a clayey soil, or if the C is negligible and the phi is predominant, then we know that the soil is a sandy soil. Okay. And because of these reasons, these variable moduli models have not become very popular, and then just about slightly before these variable moduli models came into being, in 1963, Yambu started working on expressing the relation between the shear modulus, the initial modulus of the soil and then the confining pressure. So, he looked at a lot of test data from triaxial compression tests. Then he gave an equation that the initial modulus can be expressed as some constant Ke times sigma 3 to the power m, where sigma 3 is the confining pressure, and then the Ke is a constant, Ke and m are constants. But then if you see this on the left hand side, we have a modulus, on the right hand side we have the stress, and the units for both the modulus and the stress are the same. But then we have these two parameters Ke and m. So, these Ke and m, they have to have some units, because our left hand side and the right hand side should have the same units. So, this particular equation is not it's actually dependent on the dimensions that we use. The K and m, they are not absolute constants, but they depend on the dimensions that we use. So, later this equation was modified into a non-dimensional form by writing it like this: Ei is Ke times Pa times sigma 3 by Pa to the power m. So, actually it is basically the same equation, but slightly rewritten by introducing an atmospheric pressure Pa, and now the sigma 3 by Pa is a non-dimensional constant. So, our m is non-dimensional, and then our Pa has the same units as the modulus. So, our Ke is also non-dimensional. So, our Ke and m, they are non-dimensional, and they can be used in any system of units. So, once you determine the K and m for a data given in one system of units, let us say FPS units, can use the same K and m even in the SI units. And only thing is this Pa, the atmospheric pressure that we have, should be expressed in that particular units. So, for example, in the SI units, Pa is approximately 102 kilopascals, whereas it is about 14 psi in the FPS units. And if m is 0 in this equation, your Ei becomes constant. So, that is the advantage by choosing different parameters, we can make the modulus constant during the analysis. And Kondener, he proposed a hyperbolic relation between the strain and then the deviator stress. So, he looked at all the data that we get from triaxial compression test, and then like typically our loose sand has a stress strain behavior something like this. On the x axis we have the axial strain, on the y axis we have the deviator stress, and asymptotically the deviator stress will go on increasing with strain, that is for an ideal loose sand, and at a very large strain it could reach some asymptotic limit, and that limit limit where it is achieved may be beyond our experimental range of strains. Say for example, if your laboratory apparatus can perform only strains up to about let us say 15 to 20%, and sometimes for some soils within that 20% strain you may not be able to achieve your peak stress or the limiting stress, and the sigma 1 minus sigma 3 ultimate is actually it is an asymptotic limit, whereas the sigma 1 minus sigma 3f is the failure limit that we define based on our own limitations. And Kondener, he gave this relation that deviator stress is epsilon by A plus B epsilon, and this is a typical hyperbolic equation, and this A and B they are constants, but then they have some meaning, and that we will see. And then there is they defined one ratio called as failure ratio RF as sigma 1 minus sigma 3f by sigma 1 minus sigma 3u, and this is actually the sigma 1 minus sigma 3f is what we determined from the laboratory test, and this ultimate stress is a theoretical limit that could be achieved at a very large strain, and for ideal loose sands this ratio will be more than about 0.9, and for a dense sand it could be very low, about 0.5 to 0.6. And for a dense sand, if we try to fit a hyperbolic equation, it is something like this. We can only fit this hyperbolic equation only up to in the hardening part, and beyond that your stress is going on increasing, but then your laboratory determined deviator stress will continue to fall in the strain softening part. In this case your failure ratio RF could be in the range of about 0.5 to 0.7, and we only represent the initial part of the stress strain behavior of the dense sands through this hyperbolic model. And what are these A and B? We can easily guess by reformulating this equation as A plus B epsilon is as A epsilon by sigma 1 minus sigma 3, and if we plot a graph between epsilon on the x axis and then epsilon by sigma 1 minus sigma 3 on the y axis, and if it is a truly hyperbolic behavior, all the data points should fall on a straight line like this, or in the worst case they will all be falling very close to this line, and then we can fit a best fit line, and the intercept on the y axis is your A and the slope is B. That is what we can easily see from this equation, and so as epsilon tends towards 0 or at the start, your A tends to initial inverse of the initial modulus. So, actually as epsilon tends to 0, B epsilon cancels out on the left hand side, and on the right hand side we have epsilon by sigma 1 minus sigma 3, that is the inverse of the initial modulus. So, our A, that is the intercept on the y axis, is the inverse of your initial modulus, and then what is the slope of this line B. So, as epsilon tends to infinity, the effect of A can be neglected, and then on the right hand side you have epsilon by sigma 1 minus sigma 3, and that could be ultimate, because we are dealing with ultimate limit state, or at very large shear strains epsilon gets cancelled out and your B tends towards 1 by sigma 1 minus sigma 3 ultimate. So, the B is the reciprocal of the ultimate stress or the asymptotic limit on the deviator stress, and A is the reciprocal of the initial modulus. So, this is the meaning of these two terms A and the B in the hyperbolic model. And Kondener, he just gave this equation and said that you can represent the stress strain behavior of the loose sands and then the normally consolidated clays using this equation, and beyond that he did not go, but in the year 1971 Duncan and Chang, they have taken this model and adapted it for finite element analysis. In fact, the finite element analysis became quite common by late 60s. Then at that time people were looking at different methods of modeling the nonlinear behavior and then the ultimate strength of the soil and so on. And Duncan and Chang, they have slightly modified this hyperbolic model suitable for finite element implementations, and they defined the Young's modulus, tangent Young's modulus, as dou sigma by dou epsilon. This is just basically the tangent slope of the stress strain curve, and if you differentiate your hyperbolic equation epsilon by A plus B epsilon with respect to epsilon, we get A plus B epsilon minus B epsilon and divided by the square of the denominator, and this comes out as A by A plus B epsilon. And so, in this equation your tangent modulus is A by A plus B epsilon and the whole square. It is a very simple equation, and as the strain is increasing, your shear modulus is going to reduce, because that is what is meant by this denominator, the epsilon being in the denominator and also the square. You will get a rapid decrease in the modulus as the strain increases. But then philosophically speaking, what is strain? See, for defining strain we require some initial state, and unless you know the initial length you cannot define your strain. Like the strain for a one dimensional case is the length minus original length divided by the original length is your strain. Similarly, for soils, if you want to define strain, you require some initial state, and that is impossible to get now, because the initial state will correspond to some long time in the geological past, and that could be millions of years depending on the soil strata. And so, it is better to remove your strain from this equation, and so it is, and then we can actually use our governing equation, the fundamental equation, to replace epsilon by other terms. So, by rewriting this equation, your epsilon can be written as A times sigma 1 minus sigma 3 divided by 1 minus B times sigma 1 minus sigma 3, and we can take this epsilon and substitute here, and then we will get a very interesting equation. Tangent Young's modulus is A by A plus B epsilon whole square, and epsilon is this from our fundamental equation, and so your AB A times 1 minus B sigma 1 minus sigma 3 plus AB sigma 1 minus sigma 3. So, if you simplify, you will get A by this whole square, and so your tangent Young's modulus is actually this denominator will go to the numerator because it is 1 by denominator. So, 1 minus B sigma 1 minus sigma 3 whole square divided by A, because your A square is here and A is there. So, A is there, and A means the inverse of the initial modulus. So, in fact, our ET can be written as EI times 1 minus B sigma 1 minus sigma 3 whole square, and our B is related to failure ratio RF. So, RF is sigma 1 minus sigma 3 F by sigma 1 minus sigma 3 U, and our B is sigma 1 by sigma 1 minus sigma 3 U. So, that is RF by sigma 1 minus sigma 3 failure. Okay, this is the limiting deviator stress, and our sigma 1 F can be related to sigma 3 C n phi through our Mohr-Coulomb relation, and if you subtract sigma 3 from the right hand side, you can simplify this equation as 2 C cosine phi plus 2 sigma 3 sin phi by 1 minus sin phi, and our initial modulus EI is Ke times Pa times sigma 3 by Pa to the power m, and by substituting our equation for sigma 1 minus sigma 3 F, and then our RF, we get the tangent Young's modulus as 1 minus RF 1 minus sin phi sigma 1 minus sigma 3 by 2 C cosine phi plus 2 sigma 3 sin phi, this whole square multiplied by Ke Pa times sigma 3 by Pa to the power m. So, in one single equation, Duncan and Chang, they were able to incorporate the influence of the confining pressure sigma 3, and then the influence of the shear stress in relation to the shear strength. So, as the shear stress is increasing, your modulus is going to decrease. So, this is what at a constant sigma 3. So, if your shear stress sigma 1 minus sigma 3 is going on increasing, then this ratio will go on increasing, and then this is 1 minus this. So, our the bracket will go on decreasing as the shear stress is increasing, and so in one single equation, Duncan and Chang, they have given a beautiful equation that can represent the failure of the soil, because we have basically introduced the Mohr-Coulomb relation in the for the strength of the soil. So, this parameter 1 minus sin phi times sigma 1 minus sigma 3 by 2 C cosine phi plus 2 sigma 3 sin phi is actually, it is called as the mobilized shear strength. Basically, the sigma 1 minus sigma 3 F is this, and the sigma 1 minus sigma 3 is the shear stress. So, this ratio is called as the mobilized shear strength ratio, and initially in the triaxial compression test, when sigma 1 and sigma 3 are equal, this is 0, and then towards ultimate state, when we are at sigma 1 F, this ratio will be 1. Let us look at a numerical example just to illustrate what is the effect of the shear stress on the initial modulus. Let us take a soil with a C of 10, phi of 30 degrees, confining pressure of 100 kPa, and then failure ratio is 0.85, and corresponding to these values sigma 3 of 100, C and phi of 10 and 30 degrees, the maximum deviator stress as per the Mohr-Coulomb relation is 234.64, right. And let us say at sigma 1 minus sigma 3 of sigma 1 minus sigma 3 of 0, that is at the start of our triaxial compression test, our stress ratio is 0 and your initial modulus is EI, because we have this, if sigma 1 minus sigma 3 is 0, this bracket will become 1, right, and as this sigma 1 minus sigma 3 is increasing, this is the stress ratio 0.426. That means that at a deviator stress of 100, you have mobilized 42.6% of the shear strength of the soil, and at 200, 210, 234.64, we have mobilized the full strength of the soil. And if you look at the tangent Young's modulus at 100, it falls down to 0.4 times EI, and at the limit state, the E tangent is only 2% of the initial modulus. So, in a way we are able to represent failure. So, after the limit state, the Young's modulus reduces so much that your further increase of strains may not result in further increase of shear stresses. Okay. So, this is one way of modeling the failure through the hyperbolic model, and as RF is always less than 1, we will never get a tangent Young's modulus of 0. And this hyperbolic model is also a nonlinear elastic model, and it will not be able to represent the shear induced dilation, but this is able to represent the effect of the confining pressure, and then the effect of the applied shear stresses on the modulus. And this model is applicable to all the soils that undergo volumetric compression, because basically it is an elastic model. So, we cannot really represent a dilation, the shear strain induced dilation, volume expansion, and so this model we can safely apply to all the soils that undergo compression, that is our loose sands or normally consolidated clays, or even dense sand with a very high phi, but at a very high confining pressure, the soil will only undergo compression because of the suppressed dilatancy, and even at very high confining pressures we can apply the hyperbolic model, and this model is applicable at high confining pressure for very loose soils or normally consolidated clays. And the Poisson's ratio is assumed to remain constant, because there is no specific equation. Of course, there are some models with an equation for Poisson's ratio, but then I have not included those topics in this course, because we are going to see a modified hyperbolic model wherein we represent the variation of the Poisson's ratio, and because of this reason that the Poisson's ratio remains constant, the soil will undergo volumetric compression even after limit state. If you increase the strain, the soil will only undergo volumetric compression. And the determination of material properties, I think that we will see later. And now let us look at our hyperbolic equation, and let me demonstrate through one Excel Excel program. This is the hyperbolic original model. Okay, right. So, this program is a very simple Excel program that implements our hyperbolic model for determining the stress strain behavior of the soils, and the basic input that you need to give the cohesive strength C, friction angle phi, and then the confining pressure sigma 3, and then the Ke, and then atmospheric pressure, and then the exponent point exponent in the equation m, and then our initial modulus Ke times Pa sigma 3 by Pa to the power m. Okay, this is the Yambu's equation, and our incremental strain, that is the increment at which we apply the axial strain, and then the RF. Okay, we will see how to determine these parameters in the next lecture. Okay, and then the Poisson's ratio is given as 0.35, and then the volumetric strain increment is very simple, 1 minus 2 nu times epsilon axial strain. Axial strain is our incremental strain. Okay, and so initially when the strain is 0, your bracketed term is 1, that is sigma 1 minus sigma 3 is 0, that is the initial state, or that is when you apply the confining pressure. Your tangent Young's modulus is only the initial modulus, and then our stress is 100. Okay, and then as you go on increasing the strain, your stress will increase, the axial stress. Axial stress is delta epsilon times E tangent. Okay, and you see here your tangent modulus, initial modulus is 25,198, and then it is gradually reducing as your strain is increasing and your stress is increasing. In this particular case, your maximum sigma 1 is 334.64. Okay, and so here we see at an axial strain of 0.02, our axial stress is 314, and then if you look at the tangent modulus, it is gradually decreasing. Initially it was 25,198, then it has decreased to 8,989, 5,184, 3,463, 2,506, and so on. It is decreasing as your stresses are increasing. And then if you see this, basically our maximum sigma 1 is 334.64 as per our Mohr-Coulomb relation, but then our stress is going on increasing because our RF is 0.75, and because of that the bracket is never it will never become 0 unless you give it as 1. Let us say I give it as 1. Okay, and after failure, so as you are approaching the shear strength, your tangent modulus has reduced so much, and your further increase of shear stresses will decrease, and after some time, after 334, we will see that actually it requires a very, very large number of iterations, because beyond certain stress it is not increasing. Like for example, if I look at the stress strain equation, see here it is initially it is increasing very fast, but beyond that it is increasing, the shear stress is increasing very gradual, and it has gone up to about 325, that is still below our yield limit. Okay, And let's see, let me just show you another. Let's set it back to 0.75. Okay, and our maximum shear stress theoretical limit is 334. And if you look at this stress strain graph, you see this the initially our sigma 1 is 100, that is at the starting state when we applied the confining pressure. 100, it has increased to 225 and then 275 and so on. It is going on increasing, and at an axial strain of 20%, your sigma 1 has become 395, which is more than our shear strength of 334. It is beyond our limit, like 385. And let me see where we reached 334. I think at about at about maybe 3% strain. Let me go back to the calculation sheet. Okay. So, at about 3% strain, we have reached a failure stress of 334, but it is still the stress is increasing because our RF value is 0.75. So, our tangent modulus is never become, it will never become 0. It is always some value. See, it is the tangent modulus, even at very large strain, it is not 0, and because of that you will get some increase in the shear stress. And let me just increase it to 0.9 just for illustration. So, here we will see that, see, the slope will reduce. Okay. And let me just give you an extreme example. Let us take an RF of 0. So, what will happen with an RF of 0? We should get a straight line, and let us see whether we get that. Oops, sorry, I think the program is not able to plot it because your incremental stress will go on increasing, and then the total stress is too high. It is your RF, let me just take it some value of 0.5, and then you see that you get significant slope, and because of that your shear stress is increasing much beyond your shear strength. Then if you look at the volumetric strain, the volumetric strain continues to increase. The soil continues to undergo volumetric compression with increasing axial strain, because your Poisson's ratio is constant and the slope is constant all through, even during the critical state. Okay. And that is what we see. This is all in the critical state. Let me just let me put it to some reasonable value of about 0.85. Okay. So, any stress beyond 334 is in the critical state or the limit state, and we see that our axial strain continues to increase. It has not stopped. Sorry, the axial strain is increasing, and then even the volumetric strain is increasing in the compression direction. Okay, that is what we see here. Okay. So, this original hyperbolic model, the way we have it, it is not able to represent the constant volume state after the failure, although it is very good in terms of limiting the yield stresses to some value based on our Moore-Coulomb limit. So, this is the major limitation of the original hyperbolic model, and we will see in the next lecture how to incorporate the effect of the tangent Poisson's ratio in our analysis. So, that we will do in the next class.